Time for some e-learning with Miss Atkin. E-learning with Miss Atkin. E-learning with the puppy. E-learning with Miss Atkin. Yeah. What's up, scholars? Today we're talking about polygons. Now, what does this word mean? Now, poly means many, and gon means side. So we are talking about many-sided figures. Now, there are some rules about what the sides can look like. So let's draw a polygon that has 5 sides, and those sides have to be segments. They cannot be curvy, and those segments cannot cross each other. Let's give all of these vertices some names. A, B, C, D, and E. So each one of these corner points is called a vertex. Ooh, my E and my, there we go, vertex. And if you have multiple vertexes, we don't call them vertexes, we say vertices. So A, B, C, D, and E would all be vertices. A, B, C, D, and E are vertices. That's the plural form. And then all of these segments are the sides. And like I said before, the sides cannot be curvy, cannot be curved, and the sides can't cross each other. Sides cannot cross each other. Now we name the polygon with all of its vertices in order. Now it could be any order we want, so we could call this polygon A, B, C, D, E, or we could call it C, D, E, A, B, or we could call it E, A, B, C, D. It doesn't matter as long as we go in order. So we could not call it A, D, B, E, C. No dice. Okay? So name polygons by listing their vertices in order. So for example, the guy above could be A, B, C, D, E, or we'll just give one more example, D, E, A, B, C. Cool. Now you notice there's no symbol for polygon. It's just the vertices listed in order with no commas or anything. All right, cool. Now let's draw a bunch of different shapes and decide if they are polygons based on the rules that we just talked about. All right, here are our shapes. We've got A, B, C, D, E, and F. And we're going to decide if these are polygons. A, made up of only segments. Those segments don't cross each other. So yes, we're good. B, made up of segments. Those segments don't cross each other. Cool. C, same deal. Made up of segments. They don't cross each other. Great. D has a curved side. So nope. Curved side. E is made up of segments, but they're not closed together. So that's not a polygon. Not closed. It's got a little gap there. And F has sides that cross each other, so that is also not a polygon. Sides cross. All right, cool. Now above we said we name polygons by listing their vertices in order, and different polygons with different number of sides have a special names. So let's talk about all the special names for polygons based on their numbers of sides. All right, a lot of these you already know, which is great. A polygon that has 3 sides is called a triangle. A polygon that has 4 sides is a quadrilateral. Quad, meaning 4, lateral, A 5-sided figure is a pentagon. This is a government security building as well. A 6-sided figure is called a hexagon. A 7-sided figure, not super common, is a heptagon. Heptagon. An 8-sided figure, like a stop sign, is an octagon. A 9-sided figure is a nonagon. A 10-sided figure is a decagon. You can think of like decade, 10 years, dec. A 12-sided figure is a dodecagon. And these are all of the polygons that have special names. You'll see we skipped over 11 and then we stopped after 12. Now, if something has more than 12 sides or has 11 sides, we call it an n-gon. So for example, we had something that had 13 sides, that would be called a 13-gon. Or something that had 25 sides would be a 25-gon. Cool. We also have some special names for polygons that have all of their sides equal, or all of their angles equal, or all of their sides and all of those angles equal. So let's talk about those special names. There are 3 special terms: equilateral, equiangular, and regular. Equilateral means all sides are congruent. All sides are congruent. And equiangular means all angles are congruent. And a regular polygon is one that fits both of these categories. It's equilateral and equiangular. Has all of its sides and all of its angles equal. Alright, so let's draw some pictures of some shapes and decide if they are equilateral, equiangular, or regular. Okay, so we're going to name these polygons equilateral, equiangular, or regular if they are both. Now we're going to trust the markings on these pictures, not my drawings. So this guy has 5 sides, so it's a pentagon. And all of these sides are marked congruent, so it's equilateral. So this is really an equilateral pentagon. That word should come first, so I didn't leave myself a lot of space. Equilateral. And we see we have 2 right angles here, but nothing else is marked. So it is not equiangular and it is not regular. Alright, how about this guy over here? See, we've got 4 right angles that are marked, so we know it's equiangular. These 2 sides are marked congruent, and these 2 sides are marked congruent, but not all 4 sides are marked congruent, so it's not equilateral, so it's not regular. And it's got 1, 2, 3, 4 sides, so this is an equiangular quadrilateral. And this guy will have a special name. We'll talk about that later. It'll be called a rectangle. Yes, very nice. There's one other feature of polygons that we're going to talk about here, which are called their diagonals. Diagonal of a polygon. So a diagonal connects 2 non-adjacent vertices. Connects non-adjacent, meaning they're not next to each other, vertices. Alright, now let's draw a hexagon that has 6 sides. Doesn't matter if it is equilateral or equiangular for these purposes, and we're going to see how many diagonals we can draw. So, to do this, I like to start at one vertex and draw all of the diagonals I can, and then move on to the next one. So from this vertex, we can draw 1, right? So I couldn't draw that guy, because those are adjacent vertices. They're right next to each other. But that vertex is not next to that one, so I can draw that. So I got one there, and one there. So far that's 3. Let's just put little numbers next to them so we don't forget. 1, 2, 3. Now I'll move on to the next vertex. I can draw one here. That'll be our 4, our 5, and our 6. 4, 5, 6. Move on to this vertex. I've already drawn that diagonal, so we won't redraw it. We'll have 7 and 8. It's getting tight in here. 7 and 8. Move on to our next vertex. We've already drawn that diagonal. We drew this diagonal. So 9 is all we can do here. And then that vertex has everything that could be drawn, or every diagonal that could be drawn there, and same with that last one. So we have 9 diagonals in a hexagon. Fabulous. Next, we're going to talk about how quadrilaterals are kind of like circles. So go ahead and draw yourself a quadrilateral, any 4-sided figure. See, it looks kind of like a circle, right? No. Why is it like a circle? Well, a circle has 360 degrees. And the angles inside a quadrilateral also add up to 360 degrees. So if this is angle 1, angle 2, angle 3, and angle 4, the measure of all of these angles run off the page yet? We're doing good. Add up all those angles, you'll get the same amount of degrees you would in a circle. 360 degrees. Cool. This is called the interior, because it's on the inside, interior angle sum, because we added up a bunch of angles. Interior, with an R, angle sum of a quadrilateral. Fabulous. I think it's time for some example problems. So here's our first example. We have a quadrilateral, EHGF. We are told that the measure of angle E is 55 degrees. We are told that these two angles are equal to each other. One more thing I was supposed to add in the picture. H and F are congruent to each other too. Okay, so make sure you got your diagram fixed. E and G are congruent, and H and F are congruent angles. Okay, cool. So, right off the bat, we know E and G are congruent, so that means they have the same measure. And we know H and F are congruent, but we don't actually know what they are. What do we do when we don't know what things are? We call them X, right? So let's call that angle X, this angle X, and we can solve this for X by saying that all 4 of these angles are going to add up to be 360. So we've got plenty of space over here. Let's do the measure of angle E, 55, plus the measure of angle H, which is X, plus the measure of angle G, which is 55, plus the measure of angle F, which is X, equals 360 degrees. So if we add our like terms, we get 2x plus 55, and 55 is 110. We subtract 110 on both sides and get 2x equals 250, and divide each of these by 2. We have x equals 125 degrees. Fabulous, darling, fabulous. We've got 2 more examples. So here in this picture we have a quadrilateral, JMLK. Our mission is to find the measure of all of the angles and decide if this polygon is regular. What did regular mean? It meant all the sides were congruent and all of the angles are congruent. So right now we have All the sides are congruent. That's a good start. We see that these two angles are congruent to each other because they're both x. We know that guy is 80. Don't know that one off the top of our head, but it's a possibility. Let's see what we can do here. So we already know the measure of J is 80 degrees. And we know if we add all of the angles up, they'll add up to 360. So 80 plus x minus 20 plus x equals 360 degrees. If we add all our like terms, we got 3x. 80 minus 20 is 60 equals 360. Subtract 60 on both sides, and we get 3x equals 300. Divide by 3, and we see that x equals 100, which means the measure of angle M is 100 degrees. The measure of angle K is also 100 degrees. And L is x minus 20, so 100 minus 20 is 80 degrees. So going back to this question, is quadrilateral JMLK regular? No, it is not equiangular. All of its angles are not congruent to each other. In fact, we'll talk about this later, but this shape, where it has all of its sides congruent and opposite angles equal to each other, is called a rhombus. And the only regular quadrilateral is going to be a square. A square has all of its sides equal and all of its angles are equal to 90 degrees. But this guy, nope, it is not equiangular. All right, last example. Are you ready? I'm ready. Here we go. Let's bring it home. We've got a quadrilateral. It has a right angle, which we know is 90 degrees, a 60-degree angle, a 150-degree angle, and a 3x degree angle. So we're going to solve for x by adding all of these up and setting them equal to 360 degrees. So we've got 90 plus 60 plus 150 plus 3x equals 360. If we add all of our like terms, 90 plus 60 is 150 plus 150 is 300. So we have 3x plus 300 equals 360. Subtract 300 on both sides. 3x equals 60. Divide by 3, and we get x equals 20, which would mean that that angle here is 3 times 20, 60 degrees. All right, scholars, that's it. I love you. I'll see you next time. We're almost done. Keep